I invite you for the second lecture from Computer Architectures course, and today's topic is integer numbers encoding, and we extend it from the simple binary to even to the signed numbers, positive and negative, and then we switch to floating point numbers, and then we follow with the seminar where we will practice the work with those number representations and so on. So, okay, so we start with integer numbers, and the repetition from the last lecture. We have introduced a bit as a single logical value or unit of the information, which can or which value has only two states, and it is true and false. And we have seen that we can represent it even by... Okay, very strange. Do you hear me? Or no? It seems that it is running. Okay, so we can represent it by the voltage, or maybe in the optical cabling we can use, for example, the light to represent the state of the bit value and so on. We can send them serial way, one after another, or we can run more bits in parallel to form some bytes or some longer logical values vectors. And if we define that each of those bits represent a different weight, different power of 2 of the sent data, then we have found that we can use these parallel wires to send some arithmetic value in the fact. And we have seen that we can encode unsigned integer values, easy way, and if you look at it from the point of view of theory of information, then if we have n bit signals, then the total number of symbols which we can represent is 2 power n. It is simple. Problem is that if we want to represent 0, then we have in the fact one less values for the non-zero, for the positive values. So we can express values only to 2 power n or k bits minus 1 from 0 in this range, including the limits. And we see that we use so-called position place value notation. You are used for it even from the decadic system, that if you write 3, 5, 2, 1, that it is, the first one is 3 multiplied by power 0, 1, 2, 3, 10 power 3. This one is, so it is 3 multiplied by 5, plus 5 multiplied by 10 power 2, plus 2 multiplied by 10 power 1 plus 1. You know, there is nothing fancy on this. But it is important to understand that it works this way. We have used this representation to implement addition operation between two non-negative numbers. And we have seen that even this simple operation is quite complex, because it requires to propagate carry. If you do, for example, a logical AND or OR on multiple bits, then it is easy, because you can parallelize it very easily, because each result depends only on the corresponding input bits. But at the moment when we use with addition, then there is that carry, which needs to be propagated from the left to the right in the logical value, position value representation. We have introduced logical bit shift to the left and to the right. Logical shift to the left in that grading of different digits is in the fact corresponding to multiplication by 2, and shift to the right division by 2, or if we shift it by more bits, by power of 2. And the current lecture topic, we define the ranges which can be represented by those binary values. We look at multiplication and division of integer in non-negative form. Then we introduce the signed numbers, how to encode some wider range, including negative values. And we look at arithmetic overflow, and then I hope we fit at least start of real numbers representation, which is topic for your first homework and for a seminar. Now we look at C-language standard, and for non-negative integer numbers, we use unsigned char, unsigned short, long, and long. Those are guaranteed by the standard, and you can see that the maximum value which can be represented is 255, which is expected for the char, but for the integer you usually expect that it is a bigger value. But this is the one which is guaranteed by the standard. So even if you implement, for example, C-language compiler for 8-bit computer, then it cannot hold one integer value in single register. But if you implement the arithmetic to hold the values in 2 consecutive registers, then you still are compliant with the C standard. For long, it is for, milliards. So about 2 GB units, so 2 power 32 minus 1. And for a long, it is required that it is at least 2 times longer. In the fact, most of today computers use integer of size for 4 bytes. So in the fact, integer is same as the short, as the long, excuse me, and in the standard minimum value. And if you work on 64-bit computers, then usually long is 8 bytes. But be careful, for example, on Windows, it is even on 64-bit, long is only 4 bytes, which is big problem if you cast a pointer to the long and back, which works on 32-bit Windows, and on 64-bit it doesn't work anymore. In the fact, standard of C language doesn't require that the numbers are internally encoded in the binary system. So standard, even it doesn't require, it requires that there is possibility to do binary masking on the unsigned integers, but it is not required for signed. So for example, computer which is based on ternary system, not a binary, can be implemented such way that it fits to C language. I think it is not possible easily done for C++, but for C it is possible. Same for the byte, because we usually think that byte is equivalent to the 1 character, but you can have a DSP processor, for example, for some cable modems, which internally works only, for example, with 20 bits characters, integers, and long has to be, according to the standard, 40 bits. But it is possible, so it is not common. For most of your whole life, you will work with the computers, probably which has a addressable unit, 1 character, equivalent to 1 byte, but it is not necessary. So if you want to find the exact number of addressable units which are used for a given type, then you can use a size of operator in C. And if you want to know the actual arithmetic maximum value which you can store in unsigned integer, then there is defined macro uint max in the limits h header file. If you need to represent the exact values, for example, you want to serialize some data and you need to agree with another system which can have a different width of the registers and in the theory different definition above those minimum ranges defined by C, then you should use those types in a std int h, where you can specify exact number of bits which you want to have for a given type. It has a problem that if you try to define a type which requires 8 bits on the system which doesn't have addressable unit of 8 bits, then you cannot compile the code. And sometimes, for example, on an ARM, if you defined char or 8-bit integer, then some operations are slower because they has to be masked to the 8-bit. Then if you use a standard operation for 32-bit values. So for this reason, there are defined another type, and it is fast integer type, unsigned and signed, we get to that later, which represents or which allows to fit at least a given number of bytes. But if it is not optimum to represent the data this way, and it is better to use a wider register, then the compiler can freely choose a best matching value to speed up the computation. Same for at least. This can be a smaller and not so performant like the fast type, but sometimes it works to set even this way. Again, those are corner cases, but when you push for the last bit of the speed, then it can help. Okay, for non-negative numbers, literals in the C language, you know that you can write in the source code a decimal number, but it has to start with non-zero digit. Because if it starts with the 0 digit, then for historical reason, it represents the octal numbers. If you want to write hexadecimal numbers, then we do not have in our standard alphabet or character set enough digits to get the values from 0 to 15. So for this reason, we use A to F as the extension. And the information is prefixed, the string is prefixed by 0x, and this means that it is hexadecimal encode. Then there is the extension to write directly binary encoded numbers, which sometimes help if you write some mask and so on. It is sometimes easier to write it like this. It was GNU compiler extension, but today it is in C++ standard, and it is even in the new C standard. So there is example 252. Does it fit into the char, standard unsigned char? Yes, because the limit, typical limit for a standard unsigned char, and even a requirement from the standard is 255, so 8 bits. We can write the same value in the hexadecimal. Hexadecimal has big advantage that each digit represents how many bits? No, 2, no, 4. 4, because this is value from 0 to 15. So in the fact, 16 combinations, and 16 combination logarithms 2 of 16 is exactly the 4. Or we can write it in octal. It was used in the past when you have only a numeric keypad and you have only the numbers from 0 to 9, then it was easier and you did not need to convert it between decimal and binary representation. So it was 3 bits per digit, or you can write it as a binary number. And hexadecimal number representation has big advantage for us that basically we know that 2 nibbles, so 2 4-bit digits, form a single byte. So it is very easy to divide it to the individual bytes. So we see that this one has 6 digits, so it has in the fact 24 bits, even that we do not need for this number exactly 24 bits. It is 20 plus 1 bit to the most significant digit. But anyway, we usually round it up to 32 bits in our system, so no problem. Okay, if we store a non-negative number or unsigned number in the memory, then there are 2 options. I think that we have already shown it at the last seminar. So basically, we can start from the most significant digit and put it on the address where the variable space for given variable starts, then take another byte and follow and so on. This way. So it is called so-called big endian. It is based on a Gulliver journey. If you know Journey of Gulliver, the tale or film or book, and a little endian. In the fact, there is no big technical reason for one or another one. It works almost the same way, but there was different companies which, and even sometimes religious fights and wars for this. If you look at technical basis, then for a big endian numbers, it is easier to compare them, because if you do not have, for example, if you need to compare 2 very large numbers, for example, 256 bits numbers, large numbers, then you do not have instructions usually to compute this. And if you compare it from the most significant bits to the least significant bits, then at the moment when you find the difference, you know that you can stop. Because at the moment in the comparison when there is difference, then you know that one is bigger than another and you do not need to compare. It is same as if you compare, for example, text strings. On the other hand, if you want to add 2 large numbers which do not fit in the single register, so you need to, for example, represent them and operate with them in 4 registers, then what you need to do? You need, if this is LSB, a low significant byte, and MSB, then you need to do addition of the least significant 2 together, standard addition, and what we need to do to continue with the more significant bytes. We need to pass carry. So basically, in this case, if we start with 2 pointers on very large numbers and start from the least significant byte or word, then it is faster. At the start, the companies like Motorola and IBM and mainframes computer was typically big endian. Intel came with little endian, even that they have some processors used in the military and space, which was big endian as well. And for communication, a standard order on the internet is usually network order defined as big endian. On the PCI and PCI Express, typically a little endian is used. So you need to take care about this. And you need to, both sides has to agree on the endianing. if they serialize data or they need to send before a data some flag to say in which endian they will exchange the data. RISC-V was or is a big endian as a modern RISC system. MIPS was big endian, but later versions switch it even to the little endian. So if you have, for example, some small wireless router, then MIPS architecture is not that in this segment. It was used in supercomputers in the past and animation farms and so on, but still today you can find it in some wireless routers and so on. And usually in those contemporary devices, it is not big endian, but little endian. And sometimes you have formats like a famous Bitcoin, where the cryptographic signature is in the network order, so big endian, but actual transaction hash is in the little endian. Something can be a result of the way how it was built from some libraries. Sometimes it can be even optimization, because sometimes, for example, if you do a network routing, then if you get a first part of the target address, then you already can decide if it is most significant part, on which subnet you want to send it. On the other hand, if you get least significant bits inside a network, even inside the given segment, then you need to wait till you get a whole address. So it is interesting, and today most systems are little endian. Now we try to do something with a multiplication. And you probably know from the basic school how to multiply in decadics. So if you want to multiply 153 by 45, then we take the 5 as the least significant digit of the multiplier. We multiply a multiplicand by this value and get this result. It is easy. When you want to multiply the rest, the another digit, the 4, then we know that 4 is multiplied by 10. So basically we need to first take the value, multiply it by 4, which is easier, and then to multiply it by 10, but multiplication by 10 is in the fact, in the decadic system, shift to the left, one position left, so we put it here. And then we need to do the sum, which we have seen that it is complex operation, and there is even problem that we do not need to sum only the size of the initial inputs, but in the fact, so many digits as is sum of those two. If we multiplied 999 with 99, then we in the fact can get something like 99899 and so on, and it would be five digits. And exactly same problems apply to the multiplication in binary, but it is a little easier because in binary we know that multiplication by a single bit is only a logical masking. We take a value or we mask it to the 0. So it is much easier. In this case, we know that there is the first one, so we multiply the value by 1. Then there is a 0 here, so we take the value, multiply it by 0, and we know that the 0 is at the weight 2 power 1. So this means that we need to shift it to the left by 1. But it is 0, so there is no problem. Then we have this another one. We take this another one, take the value, multiply it, but in this case we need to shift it to the left by 2 positions. Easy, I hope that there is no problem. And then there is the final step, which is to sum all those inputs. And problem is that if we multiply a large number, it can be quite long. But we can build such a multiplier to process sequentially the operation, and it is usually done such a way that we to optimize a number of bits which we need to keep in the memory. Then we take the multiplicand and put it into the register A. Then we put a multiplier and put it into the register B, and fill the rest of this register by zeros. And what we know, if the least significant bit of B is 1, then we want to add a value to the AC, because there is this value which should be added to the result. Then we know that we will not never need to add to those bits, because at the moment when we have solved this multiplication, we know that this one is already a bit which fits into the result. So we do not need to shift other or extend the other to more bit, but we can shift the result to the right. So at this moment, the first computed bit gets here. There is the rest of the result, and into the most significant bit we move a carry. Because if we add two numbers, we know that the result can be one bit larger than the inputs. At the moment, when we do this step, then in the next pass for the given example, we have 0. So in this case, we get there, basically we have moved the 1 here, and now we have there a 0. And 0 informs, okay, this bit at this order, basically we do not need to add. So in this case, we only pass the input to the output of the other, and this 8 is ignored for this step. And again, we shift to the right. Then again, there appears a bit which is equal to the 1. This informs, okay, take A, add it with the result, and so on. So you continue 32 times, or 64 times if it is for 64-bit numbers. And you have, for 32 bits multiplied 32 bits, you have 64-bit results. For 64 by 64, you have 128 bits result. But it is extremely slow. And the most problematic part is that final addition, because the multiplication, actual bitwise multiplication, is extremely easy. It is AND gate. So what we can do with this problem, we can look at our others, which we have done before, implemented before, and we can see that if we have a full adder, then full adder provides us 2 bits of the results, but cannot overflow to the third bit, to bit number 2, because 3 times 1, which is maximal value, is a 3. So 1 plus 1 plus 1 is at the most, or is equal to the 1, 1. So if we look at the problem and we try to add 3 numbers, then we can get a result bit, which is that bit equivalent to the propagate because it is exclusive OR of those 3. And then we get a generate, which is equivalent to the carry. And the carry goes from the bit 0, should be added to the bit 1, because it is this way. So we have added, without the combination of the carry, only simply by simple parallel logic, we have added those 3 numbers and get 2 numbers, where 1 is extended by the carry by 1 bit to the left. And what we can continue. We can again add those three numbers, and so we have got those two numbers, the propagation and carry, as a result from the three initial numbers. And now we can take the fourth number, put it below those three numbers, and again we can do a sum of the three numbers without need to take care about carry. Basically, we only note the result of the carry, but do not propagate inside the addition, and shift those carry by 1 bit to the left. And then at the final step, we need to do one full addition which propagates the carry. So basically, we add in this case these carries and the Q. And I have made a mistake here. No, it is correct. I have renamed this to RS to simplify the original option when we add two together, then two together, and again, which has a logarithmic complexity, but it will take relatively long. For 32 bits, it is 5 time additions, and if we need to add it together with something more, it is even more complex. So this way, we have built the mechanism how to add 4 numbers in a 2, 3 steps, and the last one is equivalent to the full addition. But those steps are in the fact only propagation through the single gate, so it is much, much faster. And we can use this logic even for the actual multiplication, because if we do a multiplication as a logic function, then for each bit it is only the single gate which ends a corresponding bit on both inputs. Here 0, 0, here it is 1, 0, and so on. And then we need to add them together. But if we do this clever way, how to add only the three inputs, but without the carry, if we use this carry safe adder, which provides a carry as another result, then in this case, we can simplify the addition much more. If we look at the most complex column, which is this one, which adds to need 32 values, then for the adding those 32 values, if we use this carry safe logic, then we can build this operation where we add together the 3, and at the end we have one row which doesn't fit because 32 is not divisible by 3. But it is no problem. Then we get sum and the carry bits which come from the lower part of the computation. And again, we aggregate them to the actual bit, and carry goes out from this to the more significant bits, and so on. So if we look at it, then we need to do 64 times this addition, this partial addition at the start, and so on. And at the end, we have a sum and the carries, and it has to be added by conventional adder. So at the end, we have solved that most complex column in the 8 steps, this pre-computation of the multiplication. So it is fast, and we can speed up the solution. And this one is most complex, because if we look to the structure of the multiplication, then this triangle is full of zeros. So there we have in the fact directly result, so we do not need to put this one. There we have result after two-step. One step is to compute this addition, and another one, in one step, in the fact, in the two steps, yes, because we need to add the carry from the lower part, and so on. So at the end, if we implement this adder, then we are able to multiply 64 bits through compute this sum and carry, which can be done in the something like 16 gate delays, which is very fast. And if you look at today processors, they have quite often latency for the multiplication instruction 2 or 3 cycles, but very little. So it is not much different from the addition and subtraction. Okay, the division is a problem. There is division is problem in decimal system. Basically, you need to shift to the left first, so much that the most significant bit is matching the most significant digit of the divider. Then you try to divide. If in the decimal system you get some value in the system binary, you have it much easier, because in the binary system you only decide if we if the value which you want to subtract is small or equal, or if it is bigger. If it is small, we subtract it and write 1 to the result. If it is smaller, if we attempt to subtract a value which doesn't fit, then we need to write a 0 there. So it is much easier, and we stop for the integer division. We do not go into the fractions. So at the moment, when we find, for example, that the result is 21 in this case, then we do not attempt to find if there are some fractions. We take the rest, the value after the division, as the remainder of the division, or modulo, or remainder. Modulo operation is usually this called. So you see, in this case, I want to divide 240 by 11. We find that the 11 fits 2 times to the 24. We subtract 24, get the result, remainder, divide it again, try to divide it again by 11. We see that it fits only 1 time, and so on. And then there is a remainder. And it works exactly the same way for the binary case, in the binary case. And if we want to implement the hardware, there what is interesting that we can use almost the same circuit as we use for the multiplication. But in this case, we subtract here. So we take the B as a divisor. We put a whole dividend to the both registers, because usually we want to divide 64-bit, divide by 32 bits, and we test if the result of subtraction is bigger than 0. If it is not bigger than 0, then we keep original value, and then after the subtraction, and only shift a result to the left. And this way we go in 32 cycles, and we get the result of the division. And the result at the end, a result is in the A, which is where we store if we have subtracted or not subtracted, and the AC is result of the remainder. There is necessary to take care about the last step, not to shift something incorrectly and so on. But it works such easy way. And if we reuse this register even to store the result, then it has the advantage because we know that a remainder is 32-bit, but the input value is 64-bit. And we know that each time when we compute one digit, that the maximum value, remaining value, is 1 bit less. So basically, there is a shifted in the result, and this is still a remainder, and so on. It is slow, and there exists a mechanism how to do much faster computation of the revision, but those are complex and out of scope of our subject. What is interesting that such algorithms can estimate even 2 or 4 bits per a single clock cycle, and maybe you know that there was a so-called Pentium FDIF bug in 1994, which was caused by incorrect implementation of the algorithm. It was in floating point unit, and it was not that you did not get a result, but you have got a result which was very imprecise. Instead of 20 of the relative precision, 1 divided by 2 power 23, something like 16 bits or something like that. So it was incorrect. Okay, now we want to introduce assigned numbers. And the most simple way is direct representation when we write an absolute value and add 1 bit to store the sign. But we usually do not want to extend, for example, char for unsigned char to have it 8-bit and signed char to be 9-bit. So we usually take that 1 bit from the representation. So usually we use a most significant bit in the representation to represent the bit, and the actual absolute range is a little small. But the representation in the direct format is relatively inconvenient for all operations and so on. So it is usually not used. We will see the exception for floating point numbers, but for the integer numbers it is not used. The most common solution to store signed data in the computer is the second complement. And in the fact, I would not say that it is second complement. I would say that it is a complement to a module. Because if we have some k-bit representation of the number, and it is unsigned number, then we get, because we need to, or we are able to store 2 power k combinations, but we want to add a 0, then in the fact we have range from 0 to 2 power k minus 1. So this is the range which is covered. And the first number, which is not covered by the representation, is called a module. So it is first value which you cannot represent in the given representation. And if we define that negative numbers are stored as this module value minus the absolute value of some x, then it has very big advantage, because if we add the x again to if we add the absolute value or positive value or inverse value to a given x, then we get exactly the module, but because the module cannot be represented, it overflows and we get a 0. Maybe it worth to think about this representation like a representation in the decimal system. For example, you probably know gasoline stations, those counter, mechanical counter of the digits. Have you seen it? Maybe it will be a problem in the future with the students. But you have those rings with numbers. And try to think how to represent -3 in the decimal modulo representation when we have three digits. So we can represent 999 as the highest value in the decimal system. What would be the actual representation of the -3 in this system? Module of this system is 1000. Do you see it? It is the moment when we again rotate to the 0. So we need to find the value to which, if we add a 3, we rotate again to the 0 or to 1000. So it would be 997. Do you see this? And it would work for any representation. But for the binary representation, it is much easier because we have only 2 bits. If you want to compute this inverse value efficiently, we get to this a little later, then how you would do it for the, if I ask for this complement in the decimal system for a value 5, no, okay, it is too high. It would be 257. So one option is that I take 1000 and subtract 257. But if I subtract from 0 the 7, there can be case that I need to borrow from the more significant digit. But I can, okay, it was 257. But I can subtract it instead, not from 1000, but what would be easier? From which value we can subtract each value in decimal system without any need to count with the carry or borrow. 999. So if we put there 999, we subtract it. So it is 347. And now we need to add 1 to have it to the modulo. So now we want to have it 1000. So we add the 1. So we get 744. And it is a modulo representation of the -157 in decimal modulo representation. And we can do exactly the same in the binary. So if you look at it for the positive numbers, we took the value as it is, and positive and 0, and we store it to the memory. Representation is exactly the same. For the negative values, we take a module, so 2 power k, and subtract the absolute value. So, for example, -1 in this representation has to be all ones, because for all ones, when we add the inverse element, the 1, we get a module which is 0. If we want to add a 5 with a -1, so in the fact subtract the 1, then we do the simple addition, and if you try to do it mechanically, then you find that even that we do not consider that we are working with a second complement representation, we get this value, but the most significant bit is lost, and this value is in the fact the 4. So again it works, so we can use exactly the same circuit for a signed and unsigned operation. Only there are different glasses how we look at the value, but the actual hardware can be exactly the same, which is what is used in most processors. If we look at it more theoretical way, then we can define that there is some value x, And we have some function which provides a representation of this function by some code. And we store those code again sorted by some value. So if we look at the arithmetic and this axis, we have a arithmetic value. Yeah.
Can you show how you get -10 with this two-component system?
So?
How would you get -10? How would you represent it in binary?
If -10, it would be at a bit, it would be 1, 0, 0, 0, and so on. So 10 zeros minus 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And I want to represent the 10. So 10 is 1, 0, 1, 0. 8 plus 2. So if I subtract it, it is 0. This is 1. This would be 1. This would be 0. Is it this? 0, 0 is 0. No, it is 1. No, 1. 0 minus 1 is 1, and I need to borrow 1. Borrow 1, and it is 0 minus 1 is 1, and I need to borrow 1. 1 and 1, so it is a minus 2. And I need to borrow, it should be a value, basically it should be 1, 1, 1, 1. Oh. Okay, there is easier way, because as in the decimal system, we know that most easy is to take not the module, but 1, 1, 1, 1, 1, 1, 1, 1, and subtract the 10 from it, because it is easy. So it is 1, 1, 0, 0, 1, 0, 1, 0. So we subtract this, we get, in this case, it is in the fact bit complement, so we get 1, this one is 0, in this case we get 1, in this case we get 0, in this case 1, 1, 1, 1, and now we need to add the 1. So I have it correctly, in fact, in the previous case. So now I add that 1 from 999 to get to 1000. It is the same. So basically it is 1, 1, 1, 0, 1, 1, 0. And if you look at the axis, then we can represent a value, for example, for a bit from 0 to 127, but 128 already sets the most significant bit, so it overflows to the negative value. In this case, minus 128 can be represented, and then, so basically this is the representation, this is unsigned value of the code representing the arithmetic value here. So it is AX and it is the arithmetic value. I divided in the description that arithmetic value, it is that arithmetical meaning, and the representation is what is stored in the memory. So you see minus 1 is this, minus 2, and so on. And if we have additive inverse or opposite number, we have already shown how we can get it in the fact. We can get it if we have some value and we want to get the opposite number, then it doesn't depend if it is positive or negative, but we can subtract it from the module. But instead of this complex operation subtraction which borrow from the more significant bits, we can subtract it from the module minus 1, which is easy, and then in the final step add a 1. So if we look how we can implement a subtraction, then we can implement it by the hardware, by our well-known adder, which we have already tuned in the last lecture. then add there a bit complement on the second input, and some small adder which allows to add 1. Even adding the 1 is not so easy because there is propagation of that 1 which can grow up to the most significant bit. But we can do even some little more optimization, and it is to use our adder, but with half adder on the input, so it has a carry in. And then if we want to switch between addition and subtraction, for subtraction we only need to do a bit complement of the input and push a carry 1 to the first full adder in the circuitry. So this is the structure which is typically used in the processor to implement add and subtract. And in the fact, both operations are of same complexity. Multiplication and division of two complement. For the multiplication, if we multiply two positive numbers, then the result is, because the numbers in representation are exactly the same as the arithmetic meaning, and we have multiplication of the unsigned numbers. So for the positive numbers, it is easy, and we get directly result if we apply unsigned multiplier to the inputs. For the values, when one or both are negative, then it starts to be a little more complex. Because for the representation, we see that the negative value in the fact has in the representation lost the module, because it is not here, because we do not store the module. But the value is there because actual value is in the fact module minus the absolute value, and there is problem that m and module is the, okay, so there is problem in this, so I would mod minus m, and if both are negative, it is mod minus a m is in the fact module minus m, and a n is in the fact module minus n. And what happens? This should not be there because this module is in the fact in something which should not be there from the arithmetic meaning. So if we now multiply those two representations, then in the result we get in the fact a mutual multiplication of n and this module and m and this module. So you see, if we look at it, that in the fact we have added the module to the negative number, added the module to the negative number, then we get there 2 times the module, but it is no problem because it is out of the result representation. And then we have there m multiplied by module and n multiplied by module. So if we do that final correction, that we subtract those inputs multiplied by module when another input is negative, then we can use exactly the same hardware. Another interesting thing is from this, if we need only a 32 bits from the result of multiplication of 32-bit number by 32-bit number, then do we need to take care about it if it is signed or unsigned? If it doesn't overflow, then we can use exactly the same instruction, because that part which needs to be corrected in the fact fits into the more, because it is multiplied by 2 power k, so for 32-bit result it is somewhere here. So problem is if we want to detect overflow and so on, it starts to be a little more complex, but it is so easy at the start. And for the C language, there is a typical representation which specifies the minimum ranges. But I think, I'm not sure if it is not in the standard 100. This is typical. this range. But I think that in standard it is one less, that it allows even one complement representation. Anyway, if you want to know for the concrete, for the actual current system where your program runs, those minimum and maximum, then you can ask int max, long max, min, and so on, and check if your input fits into the range which can be used for the computation. And now we will check overflow, because sometimes you want to know that your computation is incorrect. And in such case, we need to decide how to find that there is a problem. For the addition, it is easy, because in this case, we have there that one bit, which is the carry from the bit number 7 to bit number 8. So it is easy if we detect that there is carry in the addition of those numbers, then we can signal a problem. There is problem how to represent such addition with a check for overflow in the C. There was usually this processor has some instruction which allow to somehow detect this situation, but the C language has no such definition, but it has been added. That today you can do a check it addition where you get a result and two inputs, and according to the size of the inputs and size of the result, this signals overflow by a return value if there is a problem. And there is even similar for multiplication and subtraction. This has been added only in C23 version. In the older ones, in GCC and CLang, there is a built-in overflow addition with overflow checking. If you do not have the C or some built-in which allows to detect it, then how we can find easily overflow for the unsigned numbers? If the result is smaller than one of the inputs. Because result of positive or zero numbers addition cannot be smaller than a result. So it is possible, but it is inefficient to test it this way. Overflow, arithmetic overflow for signed numbers. It is even more complicated, because if we add those two numbers, then there is not, in this case, a carry from the most significant bit, and result is correct, and we get a negative result. If we add those negative numbers, then there is overflow, because we add there in the representation 1 and 1 in the most significant bit, and we get there the one which is already on the 9th position or on the position of bit 8. So we have there overflow in the representation addition, but in the fact there is no overflow in the arithmetic, because result minus 32 can be well represented in the 8 bits signed number. But in this case, if we add those negative numbers, then there is overflow in the most significant carry in the most significant bit. But in this case, it is a problem, because we get from two negative numbers, the result is positive number, which from arithmetic point of view really doesn't look well. So how we can detect this situation? You can find that in this special case, there is no carry from the auxiliary, so-called auxiliary carry from the bit number 6 to the bit number 7. But there is a carry from the bit number 7 to the 8 modulo representing bit. So if those two carry signals are different, then we know that there is an overflow. And it is same for the positive numbers. If we add two positive numbers and there is no carry from the second most significant bit and there is carry in the most significant bit, then we, no, if there is no carry in the most significant bit and there is carry in the second most significant bit, then it is incorrect. So we can count or detect overflow this way, that we check the carry from most significant bit and into the most significant bit. Or the other option, which is a little more complex to write, but maybe it is easier to understand, is that if the sign of inputs are positive and the result is negative, then for sure there is some problem. And vice versa. If the sign of the inputs are negative and the sign of the output is positive, then we have arithmetic overflow. There are even some another signed numbers representation. One is simple excess k representation. In such case, we take the arithmetic value and add some offset and get a result value which is stored as the representation. So in this case, stored value 127 represents the arithmetic value 0. Do you see it? If we try to add the representations, and okay, if we want to convert to representation, we add the offset. If we want to return back to the arithmetic meaning of the given bit combination, we subtract the offset. And the range is from minus k to 2 power n minus k minus 1, because that 1 is because we cannot reach the module. Okay, so it is the same as for the unsigned numbers. And if we want to do the addition and use unsigned other for the excess k representation, then in the fact it adds two values where we have added the k. So we have x plus k plus x plus k. But we should get y plus k, and we should get in the representation x plus k, y and plus k to be in the representation. But we have got again the k twice, because we have in both input, in both representations, we have already added the k. So when we do addition, then the result has to be corrected by subtraction of the k. And there is written as, I should rewrite it to k, because in English it is called the excess k representation. So it is mistake here. Yes, and as I have translated it from Czech language, it is incorrect. For the multiplication, it is even more complex, and it is usually not solved. There are even other representation. One representation is one complements representation. It is easier to compute the complement because you take the value and only complement each bit. So there is not that final add one to get to the second or modulo complement. This representation has disadvantage that you have two zeros, one positive, one negative, and it is possible to do the unit which corrects this by some hot one correction and so on, but it is not used today in typical application. Then there are another representation, for example, binary code decimal, where you store in 4 bits directly decimal values. It has the advantage that you do not need to conversion between the decimal and binary system, but it wastes the space because you fit, for example, in the 32-bit, you fit only the 8 digits, so at the most 10 power 8 minus 1. And in the fact, in the binary representation, you fit there 4 multiplied by 10 power 9. So you see that we fit into the 32-bit much less small range. And it is complex for the computation. But sometimes in the banking application, it was used to store the exact values and do the correct rounding and so on. And now we get to the real numbers. And we can extend binary numbers to a fraction exactly the same way as we use for decimal system. What we have there is some little problem that it is basically we can say that 2 power 0 is 1. So wait, this part, we know this part of the representation which correspond to the unsigned value. But we can add some other bits which are behind a binary point and which represent the halves, quarters, eighths, and so on. So basically, for those on the right, we say that it is 2 minus j of the position, or it is in the fact equal to 1 divided 2 power j. So it is easy. It has one significant disadvantage that we cannot represent in this system, for example, 1/10. We get to this a little later, but it is a big problem that the fraction, decadic fraction, cannot be easily represented. We can have even some another fixed point real numbers representation similar to XSK, where we multiply all values by some constant. And in this case, we can, for example, count easily with cents, because we use unsigned numbers for all values multiplied by 100, and we do not have problem with conversion between binary and decimal fractions. So it is one option. Then if we do a multiplication, we need to do some correction and so on, so it gets a little more complicated. If we use a fixed point binary representation and the multiplication factor is power of 2, then it is easy that correction after multiplication is only shift right and to the left after the division. So again, it is easier to use it this way. Sometimes there is a special case when we need to represent values in the half open interval from 0 to 1. It is quite often necessary in the control, or if you want to do some attenuation of the colors and so on, you can use this representation. And in this case, it has sometimes a better resolution and use of the bits to store the value than another representation. So sometimes it is used, and even the multimedia instruction in some processors has support for that fixed point fraction numbers, for example, for the color correction and so on. Okay. If we want to do the operation, then as I have said, it is necessary after the multiplication. If we do addition, it is the same, because both numbers has been multiplied by the same factor. So the result is again multiplied by the given factor. But if we do a multiplication, then we need to do the correction. If we do a division, again, we need to multiply it by power of 2, or that constant which is used to define the fractions. And now we get to the actual topic of our seminaries, and it is a floating point real numbers, which is what you use most time in the computers. Sometimes it has a limitation. So why we do in so deep depth into the floating point numbers is to understand the limitation. Because, for example, multiple missions to the space has fault on the resolution of the used representation and so on. It is because it seems that it works, and at some moment some value, if it gets too big, starts to lose the resolution, and you can get totally incorrect results. It is, for example, interesting if you do a numerical simulation in MATLAB Simulink that I have got in some system with dry friction, to the result that Simulink has written the table, the computation overflows required available precision of the double, and the result cannot be determined, which is great result because it at least informs you that there is a problem. Much worse are situations where internally the computation degrades and you do not get any error, exception, a way to react. Okay, anyway, if we have a decimal number and we want to write it some reasonable way on a limited number of digits, with a limited number of digits, then we use so-called scientific notation. This requires that we shift a decimal point in the actual mantissa such way that only the single non-zero digit is before a decimal point, and this shift of the decimal point is compensated by the exponent which is written in the form of power of 10. You see, it is easy. If it is some value bigger than 9.999, so equal or bigger than 10, then the exponent will be positive. If it is value which is smaller in absolute value, if it is smaller than 1, there the exponent will be negative. And we can do exactly the same with the binary system. So if we write a binary number and it is too long to represent and so on, we can shift a binary point to the left or to the right, such way that exactly one digit is before a binary point. But for binary point, there is one interesting feature. Which value can be before binary point if it should not be a 0? It is binary, so it has only one option. It can be only the 1. So in this case, we in the result do not need to store this one, because we know that this one is mandatory here for the value which is stored in this scientific-like representation. And there is a standard IEEE 754, which defines how to encode the binary numbers. Okay, sit down, please. Which encodes binary in the binary system floating point or real numbers. And there are in the original standard there are defined two sizes. One how to represent the value in 32-bit, and another how to represent it in the 64-bit. And in this case, we use 1 bit for the sign representation. So in this case, in the fact, we use a direct representation of the sign. Then we use 8 bits to store the exponent, but exponent is in this case not stored in the second complement, but in the excess k representation. So in the fact, it is the arithmetic value plus 127. And then 23 bits are used for the mantissa. Why is used this excess k here? In the fact, if we look at it at the table, then basically you have some range of the arithmetic values which you want to encode somewhere into some codes, into some combinations. So it is some AX representation. And this is limited. For example, it is limited to 2 power 32 minus 1, or number of combination is 2 power 32. If we define the transformation as linear, then in this case, we have a very bad resolution for the small numbers here. And if we want to have a 1 somewhere here, if we want to switch this axis to be logarithmic, then in this case, we want to, in the fact, for the relative resolution, to keep this as a logarithmic transformation. But okay, we switch back to the non-logarithmic one. And what we need to say, if we have some range for the exponent, then we can say that that exponent is from, if it is excess k and k is equal to 127, then the smallest value is minus 127, but we take this value as a special one because we need somehow to represent 0. So we take the range from, for the normalized number, from minus 126, but it is represented by a 1 in the encoded exponent. And the biggest value we reserve 255 for the for some overflow. So 254 is equivalent to, you can try to subtract 127, but it is 127. So this is the range, available range for the exponent. And now we start with very small numbers which are in the range 2 power minus 127. But we do not want with this, with some small resolution, to fill a whole coding space, because we would get only to something like 2 times this value and so on. So in the fact, we want to use only part of the representation, and then we want to lower the resolution, absolute resolution. So we want to encode the rest values which start at 2 minus 120, okay, it was 6, it would be correct, 125. Then we want to, in the fact, for those numbers, we want to lower the amount of the codes which we use from the available code space. And again, when we reach 2 power minus 124, then again we lower the resolution. Do you see? Because this way, if we do not waste for the 2 small numbers, too big part of those codes which we have available from those 32 bits, then we can keep the actual resolution, relative resolution constant. Problem is that absolute resolution change, because each time we use less and less codes for the same range of the values. Now we again represent the 2 times this this value represent by even, or in this case it is logarithmic in the fact. So it is, we get there to 1 to 123, and there would be something like 2 power 122. You see, so it starts to use less and less from the codes. So the relative resolution compared to the size of the value, to the actual absolute value of the number, is kept at the compromise that we lose the absolute precision. But it is what we want to do, because in this case, if we define that mantissa is 23 bits, then what is actual resolution? It is hidden 1 plus 23 bits, and if we that last bit set between 0 and 1, then a relative precision at this point is that small step, again this one, so it is 2 power minus 23. So it is relative, or relative resolution would be vice versa. So relative resolution is 2 power 23. So basically we know that the step at which we move on this axis is, in this case, 8 million, it is 23, yes, is 8 million smaller than the absolute value. So we know that we compute approximately at 1/4 of, or 1/8 of ppm. Do you know ppm? Per mile. So 1 millard or millionth, I'm not sure how to say it correctly in English. So basically we compute at something with relative precision, because if you want to compute a distance of the, for example, star, and count it with the size between the atoms, and compute from this, for example, some mass and gravitation field and so on, then basically you cannot use so long representations that you can fit those so long numbers with same absolute precision. But this technique with the relative precision is great. It has one big problem, that if we define that we need to keep the each time the representation with the most significant mantissa, encoded mantissa bit set, that we cannot represent a 0. Because 0 means to represent it by the exponent 2 power minus infinity. So we need to add there, and this is the reason why we keep this value representing in the fact value 0, which would represent 2 power 127. We keep it as a special case, and we define that if there is this value and the mantissa is 0, that it is absolute 0, and we lose that rule that we have to keep there the hidden 1. Okay, so it is for 32-bit. For 64-bit, it only extend, sign is still 1 bit, and it extend, and I have it incorrect, it should be 0, 1, 23 here, the excess. 11 bits for the exponent, and 52 bits for mantissa. And if we look at the actual encoding, then in the fact we store into the memory the sign, the exponent. In this case, if it is a value, for example, we want to encode this value, so this value has a first bit, non-zero bit, at the position of halves. So this means that we need to multiply mantissa by 2 and subtract 1 from the exponent. So it says it is something little more than 1/2. Okay, so the exponent is -1. We get from this exponent in arithmetic meaning to the representation in with the excess k 127. So the result is that it is 126. So we store the 126 in the following next 8 bits. Then we want to compute the mantissa, which is this part, but because this one is implicit, we can hide it and write into the mantissa only the rest of the value, of the binary value. We will practice this during the seminar. And in the fact, this is the start of the seminar at this moment. So, for normalized number, when we represent normalized numbers, so those which can be represented in the binary with that 1 at the start of the mantissa, then we can start with the exponent from -126 to 127 for 32-bit representation. And that representation will be stored as a value from 1 to 254. And then we need some values which represent the case if we do some operation which is problematic. For example, if we try to divide +10 divided by -0, what is the result? It would overflow. Or if we divide by something very, very small, that again, it can overflow. But in maths, we know that there are some overflows, and sometimes we need to compute with it. So it is a plus infinity. So this is that last code which we have there, 255, which represents the infinity. So it signals can signal some exception, but anyway, in the result, you get this value. What happens if you try to divide 0 by 0? This is a situation where you do not know if you are very far on the left, very far on the right, or near to the 0. So basically, in this case, you cannot say nothing about the result. So in this case, again, it can signal exception, and a result is not a number, which means that we do not know what happened and what is stored in the result. And there is the overview table. So we see that if the exponent is 0, then it is a special code for which if mantissa is 0, then it is exact 0. When mantissa is 0, when exponent is 0 and mantissa is non-zero, that should be denormalized. Denormalized number around 0. So those very small numbers which represent this gap. And if the exponent is non-zero, then we have there a small normalized number which can be stored. And for any value here, we get in that range where we know that the resolution, relative resolution is kept at the given value. And okay, there is the evaluated smallest value which can be the normalized number. There is smallest normalized number, and we have there biggest normalized number.